In 1905, a Swiss patent clerk by the name of Albert Einstein identified a fundamental problem with classical physics. The theory of classical electromagnetism, which concerns the interactions between charged objects, was at odds with Galilean relativity, which is about how observers measure motion differently based on their frame of reference. The problem can be understood with a simple thought experiment involving the flow of current through a wire, with an electron outside drifting along with the same velocity as the current in the wire. In one reference frame, an observer sees current moving through the wire, so they will say a magnetic field is produced, predicting that the field will apply a force on the moving electron. In the reference frame of the electron, though, it doesn't see itself in motion. Instead, it sees the wire and all of the positive charges inside rushing past. Since magnetic forces are only applied to moving charges, it will predict that no force is produced. This is a serious dilemma. You can't have two different outcomes for an event. There is one event that happens which observers must agree on. This is the logic that underpins all of science. This means that the models we use to make our predictions have to be wrong, and they therefore need to be revised. Special relativity is one attempt to revise these models, with the framework being explained in Einstein's landmark paper titled On the Electrodynamics of Moving Bodies. To solve the problem, there are two possible routes of action. Either classical electromagnetism needs to be revised, or Galilean relativity needs to be revised. Given the success of classical electromagnetism in experiment and the concrete mathematical basis behind it, Einstein chose to take a deeper look at Galilean relativity by testing it in the most extreme speeds. The most extreme speed known at the time was the speed of light. According to Galilean relativity, if you were to run at the speed of light alongside a beam of light, you would observe the light itself to be stationary, an idea allegedly dreamt up by Einstein at the age of 16. However, since light is just a repeating series of electric and magnetic fields, as shown by Maxwell's equations, this means that the laws of electromagnetism would be incorrect in your reference frame. This is a ridiculous implication. The laws of physics don't change depending on your motion. To resolve this issue with Galilean relativity, Einstein put forward two simple postulates. The first states that all inertial frames of reference are equivalent. An inertial reference is simply one in which there is no acceleration. So a frame of reference at rest is physically equal to one moving along at a constant velocity. What this means is that there is no experiment you can conduct to distinguish a frame of reference at rest from one moving at a constant velocity. This is an everyday phenomenon. If you've ever driven in a car with an air freshener, the air freshener looks the same when the car is still compared to when it's moving. Only when the car accelerates, i.e. becomes a non-inertial frame of reference, does the air freshener swing. The second postulate is another relatively simple idea, which states that all observers will measure the speed of light to be the same value, regardless of their motion. The speed of light is said to be absolute. This is at odds with Galilean relativity. If you're on Earth watching a train go by, and somebody on the train throws a ball in the direction of the train's motion, you can measure the ball's velocity as a sum of the train's velocity and the ball's velocity. The second postulate says that this idea of adding velocities is invalid in the context of light. It only applies to objects with mass. According to the second postulate, if you're on Earth watching a spaceship fly by at 90% the speed of light, and a beam of light is shot in the spaceship's direction of motion, you will still measure the light as traveling at c. It doesn't add up to 1.9 c in the same fashion as the ball on the train. Such an idea is very difficult to experimentally verify. Thus, the second postulate was a controversial idea when Einstein published his 1905 paper. But there was one key piece of experimental evidence that supported it: the Michelson-Morley experiment. The Michelson-Morley experiment aimed to detect the existence of the luminiferous ether, a proposed medium in which light propagated through. This was to be done by shining a light source towards a half-silver mirror, which would split the light beam into two perpendicular beams. One of these beams would be affected by a so-called ether wind, which would impede its motion and cause it to be out of phase with the other beam. When these two beams reflected after traveling an equal distance and then recombined, they would subsequently be out of phase, which would produce an interference pattern. However, this interference pattern was never observed, even when the experimental conditions were altered. The experiment consistently yielded a null result. This implies that the ether does not exist, and by extension, it means that the tenets of Galilean relativity don't need to be applied to light, which is exactly what is communicated by the second postulate. In retrospect, it is not so far-fetched that Einstein arrived at the second postulate. He had studied the photoelectric effect and knew that a classical wave model could not account for the complete nature of light. He knew that if physics was to move forward, new modes of thinking had to be adopted. With the two postulates established, we see that should they be true at the same time, and all evidence we have points to such a conclusion, then a variety of consequences should occur, illuminated with ease by Einstein's thought experiments. Prior to special relativity, it was widely accepted that time was an absolute quantity. That is, all observers measure the time taken for an event to be equal, while the speed of light could change in accordance with this principle. In the framework of special relativity, the reverse case is true. The speed of light is constant, while time can be measured differently by observers in accordance with the second postulate. Einstein showed that the times measured for events could change due to relative motion by means of a simple thought experiment involving a flash of light on a moving train. Here's the setup. We have two observers. One is on a moving train coasting along at a constant velocity, while another is stationary outside the train, looking in. Now let's say that a beam of light is sent from one side of the train carriage to another, and is then reflected from a mirror. If we define the length of the train carriage to be L, then the observer on the train will measure the light's trip taking a time equal to 2L over c. Time is just distance divided by velocity. Its trajectory will resemble a straight line. Outside, however, is a different story. As the light beam travels, the train will move. So if we wanted to trace out a line representing the light's trajectory, it would be bent like a triangle. Let's call the distance it travels d. Since the speed of light is constant and the distance d is greater than L, the time taken for the light's trip would be measured longer by the stationary observer when compared to the observer on the train. The time taken for the light's trip according to the outside observer is 2d over c. We can use simple trigonometry to derive a mathematical expression for this discrepancy in time. If we take the ratio of the outside time to the inside time, we can arrive at this expression, which will reduce to d over L. Using simple trigonometric identities, d over L is actually just the reciprocal of sine theta from the outside reference frame. Using the Pythagorean identity, we can make an expression for sine theta, which is the square root of 1 minus cosine squared theta. Returning to the outside observer triangle, cosine theta can be given as a ratio of the adjacent velocity to the hypotenuse velocity. The adjacent velocity is just the velocity of the train as it moves past, while the hypotenuse velocity is the speed of light, so cosine theta is v over c. Therefore, the ratio of the outside time to the inside time is this expression, which is commonly referred to as the Lorentz factor, or more simply, gamma. We can solve for t, which represents the dilated time, by moving the inside time, or more commonly known as the proper time, over to the other side, which gives us this formula. From this thought experiment, we can arrive at a simple principle. The time associated with any event in a moving frame of reference, it doesn't necessarily have to be light, is measured to be longer by observers who are moving slower outside as compared to observers inside. If we plug in any non-zero value for velocity into our new formula, there will exist a discrepancy in time, with this discrepancy approaching infinity as velocity also approaches infinity. Following on from time dilation, there is another consequence of special relativity, one involving the inertia of a body as it approaches light speed. First, however, we must understand that light has momentum, a confusing concept if one closely adheres to classical mechanics. In physics, all forces are ordained by the transfer of momentum, and all changes in momentum are ordained by forces. If something can apply a force to something, by definition, that thing has momentum. We know that when light is shown upon a metal surface, the light causes the electrons to move. Therefore, by simple causality, the light must have momentum. The problem many people have is they remember momentum not as an idea, but instead as a formula, where momentum is just the product of an object's mass and its velocity. When Isaac Newton invented this formula, he made it under the logic that an increase in either mass or velocity would result in a greater force. Since both are directly proportional, momentum should just be mass times velocity because that makes sense mathematically. In the case of things without mass though, such as light, Newton's formula doesn't work. He wouldn't have known this though since he believed light did in fact have mass, albeit small. We need to stop thinking about momentum in terms of formulae and instead of terms of its definition. Things have momentum when they are capable of applying a force. To show you that light has momentum, let's look at this electromagnetic wave. When this electromagnetic wave encounters a proton, the electric field pushes it downwards. And since the proton is now moving, the magnetic field begins to apply a force as well, which is to the right as per our right-hand rule. In the next phase of the wave, the same thing happens, but the electric force is in the opposite direction. The net effect is that the electromagnetic wave carries the proton along with it, which is virtually analogous to any other scenario in mechanical momentum, like a sliding box pushing another small box along with it. There is empirical evidence that supports the momentum of light too, seen in the night sky. Close to the sun, where the flux of light is very high, the light has enough collective momentum to apply a force to the tails of comets. This results in the observation that comet tails, which consist of ionized gases, will always point away from the Sun, due to the exchange of forces between light and the matter constituting the comet tail. The technical name for this phenomenon is radiation pressure, if you're interested or want to do some further reading. Let's imagine that there is a spaceship at rest in outer space where we are stationary observers measuring the motion of the spacecraft. Now let's say that there is a constant stream of photons approaching the ship, and when these photons strike the ship, they transfer their momentum to it, causing it to accelerate. A constant stream of photons entails a constant addition of momentum to the system, so it follows that the ship should accelerate at a constant rate. However, this assumption does not account for the second postulate, which states that the speed of these photons should be constant. Because these photons travel at a constant speed, when the ship is traveling at sufficiently high speeds, the photons will have to chase the spaceship, causing the time interval between successive photons to become longer, therefore gradually reducing acceleration. When the velocity of the spaceship is close to the speed of light, the time interval between successive photon strikes becomes very long. In fact, it approaches infinity as the ship gets faster and faster. This relationship is modeled by the same mathematical ratio as time dilation, the Lorentz factor, which, when graphed, correctly accounts for the effects of the second postulate. We see on the graph that when velocity is close to c, the time interval between photon strikes approaches infinity, which makes sense as per what was just said. When the velocity of the ship is less than half the speed of light, this effect becomes essentially negligible, because the photons are still much faster than the ship. Just to drill this point home, consider the following table. This table shows the acceleration values that we, the stationary observer, measure for the ship as it is being hit by the photons. At low velocities, this will be some value, let's say 100 km per second squared. At half the speed of light, this acceleration is reduced since the photons take longer now to hit the ship, giving a new acceleration of 86.6 km per second squared. At 99% the speed of light, this acceleration is reduced even further, to a value of 14 km per second squared. At 99.9% the speed of light, the acceleration is 4.47 km per second squared, and so on and so forth. If, theoretically, you wanted to reach the speed of light, then it would take an infinite amount of time, because the last photon to transfer the energy will have to travel for an infinitely long period of time to finally reach the ship. If you wanted to increase the energy of the photons, such that a constant acceleration is produced, then you still run into the same problem, because now an infinite amount of energy is needed. It is therefore impossible to reach the speed of light, because to do so would require either an infinite amount of time or an infinite amount of energy, two resources which are physically impossible to possess. This thought experiment shows that when a particle gets close to the speed of light, it has a greater tendency to resist changes in its motion. By definition, it gains more inertia. This gain in inertia can be effectively modeled as mass dilation, but only in a purely mathematical sense. The mass won't actually increase since the amount of matter constituting the ship doesn't change. The inertia is affected by the Lorentz factor in the same vein as time dilation, giving us this formula. Since this change in inertia is brought about due to the spaceship's speed, we should also include velocity in the equation, which gives us this equation, relativistic momentum. When cosmic rays from outer space enter Earth's atmosphere, they collide with atmospheric particles in extremely energetic collisions. These high-energy collisions produce particles called muons, which have a mean lifetime of 2.2 microseconds. We detect them regularly on Earth's surface. These muons have very little mass, so when they are produced, they are already traveling at speeds close to the speed of light. If we approximate their velocity to just c, the speed of light, then these muons will travel about 660 meters in their lifetime. For reference, these muons are produced about 15,000 meters above the ground. So how are these muons reaching the ground? In classical mechanics, physicists would have just assumed that the muons were traveling faster than light, but we know from relativistic momentum that the speed of light is the absolute limit. So what's happening? The answer is time dilation. Relative to us, events take longer in the muon's reference frame, including the time taken for the processes which facilitate the muon's decay. Therefore, according to us, it will live for longer and cover more distance. We can show this mathematically using our time dilation expression. If the muon is traveling at 99.99% the speed of light, 0.9999c, then the distance it covers is given by this expression, which gives a value much greater than 15,000 meters. So, if the muon is traveling close to the speed of light, it will travel sufficient distance to reach the ground. But there is one thing we have not considered, that of the muon's reference frame. Relative to the muon, time isn't dilated, so we lack an explanation as to how it can reach the ground. That brings us back to square one. Using the models we know so far, we have no explanation as for how an observer in the muon's reference frame can measure the same event as we can. There is only one possible explanation. The muon must be traversing a contracted distance in the proper time relative to itself, while we on Earth see it traveling the proper distance in a dilated time. This allows both observers to agree upon the event. The muon reaches the ground. Mathematically, we can depict that information like this. A grounded observer measures the velocity of the muon by dividing the proper distance L0 by the dilated time t. The muon measures the velocity at which Earth's surface rushes towards it by dividing a contracted length L by the proper time t0. Solving for L, we get this expression, but t over t0 is just 1 over gamma, giving us this equation for length contraction. This equation shows us that when a massive object of some length L0 is rushing towards an observer, it is contracted along its plane of motion. In the case of the muon, it is Earth's surface rushing up towards the muon, causing the distance between the ground and the atmosphere to appear shorter. In summary, there are three consequences of special relativity, all mathematically modeled by the Lorentz factor: time dilation, relativistic momentum, and length contraction. Now that we understand both the kinematics and dynamics of special relativity, let's return to our initial experiment involving the current-carrying wire and the outside electron. We already have an explanation for the motion of the electron from the outside reference frame. It's just the magnetic field applying a force on the moving electron. We need to reconsider the reference frame of the moving electron using our new knowledge. From the electron's perspective, the positive charges of the wire are rushing past it. However, we know now that moving objects are contracted along the direction of motion, so the positive charges appear closer together from the electron's perspective. The electron will see the wire as having a greater density of positive charges. So it will say that the wire is charged and thus an electric force of attraction is produced on the stationary electron. Length contraction solves our problem. So, in the electron's reference frame, it moves towards the wire, which is also what happens from the outside reference frame with the magnetic field. The observations are now reconciled with each other, but there's a twist involved. Similar to our muon example before, both observers agree upon the outcome of an event, yet they do not agree on what caused the event. One can argue that magnetism caused the electron to move, just as easily as one can argue an electric force did.